All right. Okay. Hey, for those of you doesn't know me, I'm Yiping Wang, professor in engineering department, and uh, thanks everybody taking time in the busy schedule to join the call. And we are going to talking about machine learning topics. In today's talk. We have a privilege have Dr. Fareed Kafizov from Verizon to give us a talk on this, the subject matter of can machines learn the meaning of the words. Okay, Dr. Kafizov is currently associate fellow at Verizon. He has worked in wireless industry for over 25 years. Actually, we used to work together. Yeah, he was one of the pioneer research on TCP/IP protocol over wireless channel. Okay, he has hold numerous U.S. patents, and his research interest is data science, math, and engineering. Okay, without further ado, we give the time to Dr. Kafizov.
Um, Hi, thank you, Dr. Wang. Can everybody hear me okay?
Yeah.
Okay, thank you. Yes, thank you very much for letting me speak to the audience here at Collin College. The topic that I will be discussing has nothing to do with my work or Verizon per se, even though this now become such an important algorithm and technology that I will touch upon at the very end, that we end up using it at work. However, what I'll be discussing, as you will see, has nothing to do with communication as such. I just learned about this sort of by accident several years ago, and first I was somewhat skeptical, but then I tried it, and I was really amazed that whatever I was reading in the paper actually is working. It was materializing, and ever since I was even more interested in the subject, and I given several talks where I covered various aspects of machine learning, and this topic was always included because I find this a very interesting topic. And it's still relatively new, although a lot of people who've done machine learning, I'm sure they know about this by now. So what I'll try to do today, cover three aspects. I will kind of outline the general idea behind the topic of whether machines can learn meaning of words. And I'll do a demo, which would be very thorough, very detailed, including all the math behind it and the code. And I'll let you see for yourself that you can actually implement it quite easily and it runs well. And then I'll jump to the main contribution, which was done by Mikolov and his colleagues at various companies at different times. But the main papers that I'll be discussing came out of Google in 2013. Again, what I'd like to do there is kind of to show you that this technique that we'll be observing can be turned into technology. And that's, to me personally, that's the most fascinating part. And I'll spend, just like I said, a few minutes discussing that because it's really, really exciting part. All right, so let's start our communication discussion on this topic, and let's try to answer some questions. So if I ask you whether machines can learn meaning of the words, I'm pretty sure everybody would say no. And what we really answering in this question, when we say no, the understanding is machines cannot grasp meanings of the words in the same way as we humans do. Sorry, I'm trying to flip my slides and somehow my machine is not following. Okay, all right. What we can do though is we need really to understand, first of all, what are we saying? What do we mean by meaning? What's the definition of meaning? Well, if it's conventional definition, as we understand in day-to-day life, then just like I said, the answer is no. However, we could alter the definition of meaning when it comes to machines, because what do machines do? Well, they work with numbers, as you know, right? Zeros and ones, to be precise. And therefore, by the word meaning here, we could say this. Can machines learn the difference between representations of words given to them? So just to be specific, every time you ask machine to do something, you give some instructions and data, everything must be in digits, and the data must come in digits. So if you ask machine to distinguish between various words, each word has to be represented as a sequence of digits. So for example, on this slide, we're showing two sentences with 14 words, and we could represent each word as a sequence of 0 and 1s. In this particular example, I've chosen what's called one-hot encoding. And the way it looks as follows. I have a sequence of 0 and 1s where all positions are zeros except single position. And that single position where I'm putting 1 is unique to each word, because I have 14 words. I have vector of length 14. So I have 1 in position 1 for the first word, in position 2 for the second, etc. Now, this is valid representation for machine. And if you ask machine to distinguish between these words now, or vector words, it would say, well, there is no difference because any two words are equivalent. They're orthogonal to each other. What we'd like to do now, we would like to rephrase our question this way. Can machine figure out how to represent words in a different way? Specifically, we would like machine to transform each of those vectors into so-called dense vectors or dense embedding in such a way that two words which are close in meaning, such as happy and thrilled, are now represented by different vectors which are closer to each other. And so in our language, we call this similar words or similarity for vectors. And when I say similarity, we're using so-called cosine similarity. And let me remind very quickly what that is. So for any two vectors, everybody knows what dot product is, right? It's a coordinate-wise multiplication and then adding up those products. So for example, for vectors 3, 5 and minus 2, 1, dot product is calculated this way and it's equal minus 1. Now that we know dot product definition, we can easily compute cosine of angle between any two vectors. And the value of the cosine between any two vectors is used as a measure of similarity. So in example that I showed you earlier, the two vectors were very close to each other, and therefore their similarity is close to 1, cosine similarity. Okay, so now that we define meaning in that way, the answer actually is yes. And let me show it to you in this example right here. So somebody already programmed machine to do what we just described. And if I type in word thrilled and ask machine to give me words which are close in meaning to that word, sorry, give me 1 second. All right, let me see what's going on. It did work before the meeting. Let me try some other word. Give me 1 second. All right, so this seems to be not working. How about this word? All right, okay, so there was some problem. All right, so what I did, I typed in word happy. And as you see in this list, there are like other words which are close in meaning, including thrilled. Okay. All right. So now, what I just demonstrated for you, yes, machine can understand the meaning of words in that narrow sense that we just defined. The question, the next question is, how do they do that? And to answer this question, first of all, I'd like you to look at this example. In this example, I'm asking to identify the meaning of word Bardywalk just by looking at the sentences listed here. Now, you may or may not the meaning of that particular word. Even if you didn't know the meaning of that word, you would still figure it out quite easily if you read these sentences. For example, when I read the first sentence, he handed her a glass of Bardywalk. What can we figure out about the word barley walk?
It's a drink.
It's a drink, correct. And then I read the next sentence. Pete staggered to his feet, face flushed from too much barley walk.
It's alcoholic.
Most likely, yes. Next one is very telling. Malbec, one of the lesser known barley walk grapes, responds well to Australia's sunshine.
It's a wine.
Yeah, it's made out of grapes. The drink made of grapes. The drinks were delicious, blood red barley walk as well as light, sweet Rhenish. Same thing, right? It's an alcoholic drink. And then I dine of bread and cheese and this excellent barley walk. Beef dishes I make to complement the barley walk. So by reading some of the sentences, even probably before we get to the very last one, it is clear that this alcoholic drink made out of grapes. All right. And the point of this exercise is very simple. We learn meanings of words by looking at their context. This is a phenomenon that has been observed a long time, even like linguists in last century, like 1957, famous quote here, identified that you learn the meaning of words just by looking at the context. And that's exactly what we're going to try to do. We will look at the context and try to answer this question, how this can be done. How can machine learn the meaning of the words? To do that, I'm going to focus now on a slightly simpler exercise for the purposes of, just to make it very clear how it's done. So a simplified problem we're going to address is going to be how can we separate words according to their relevant context. And what I mean by relevant context, I mean the following. So I've given here for you 6 sentences. If you read the 3 top sentences, you'll identify that they belong sort of to fish, ocean, water, right? And the last 3 sentences talk about skies and birds and that kind of stuff. So clearly there are 2 types of words, each belong to each of the topics in this context. And what I'd like to do, I'd like to focus on 14 words which are of interest to us. I'm discarding words in red because these are so-called stop words or noise words. They can appear in any context. They're kind of helping to form sentences. The actual words we're interested in are 14 listed as vocabulary, and there are, as you could see, not very many of them. And what I could do, I could just throw them randomly on a 2x2 plane, and they may look like this, as this, in this rectangle over here. However, my job is to design an algorithm that will sort these words in such a way that they might be separated by a straight line. Okay? Is the task clear? Are there any questions what we're trying to do? Okay. If any questions, feel free to interrupt me at any time. But basically, we're doing essentially the same thing, but it's somewhat simpler exercise. And what we will do, we will focus on the context, and from the context, we will identify for each word its neighbor, so to speak. When I say neighbor, I'm allowing myself to go in each sentence 2 steps to the left and 2 steps to the right. And that allows me to form pairs of words. For example, from the first sentence, I'll get fish as my input word, and then I would like it to be somehow close in that vector representation to word swim. And also fish must be close to word deep, etc. So we're forming pairs of words based on our context. As I mentioned, window size is 2. And if you do that, you're going to end up with 44 pairs. All right, so the task is clear. What we need to do, problem is stated. How are we going to do that? Well, just like I said, we will start with these pairs of words, 44. To begin with, I'm going to look at this one hot encoding that I described for you earlier. And I will be learning what's called better embedding. In this case, my embedding is going to be in 2-dimensional space so that I can map my words just like that, okay? And that embedding would be represented as a matrix for us. So to be specific, here's the algorithm. Here's the outline, how it's going to work. So given any pair of words, for example, bird as input and fly as a sort of label, if you like, or the words for which bird should be close, we will do the following. We will multiply X and matrix W, and then we will put that result into a product of the outcoming vector with another matrix W1. And the result is going to be vector of length 14. Let's call it Y prime. Then we will compute what we call utility function or objective function. And we will do optimization of the weights, which are elements of matrix W0. And we will do it in the loop until we arrive to acceptable result. Okay? Just in case somebody is rusty on matrix multiplication, let me remind you quickly how it works. So in this example, I simplified my matrix W and my vector X. So X is a vector of numbers, length 3. We call it a row vector. If I multiply by matrix W, in this case 3 by 2, I'm getting 2 numbers like this. And if I multiply those by additional matrix W1, which is 2 by 3, I'm getting as an output a vector of the same length with my X. All right? I'm sorry, there is some background noise. Can you please mute your microphone, if you don't mind? Thank you. So any questions about how this algorithm is supposed to work? All right, no questions, good. So I need to say a couple more words here about the utility function, and let me do it on this slide. It's a little bit mathematical, but the idea is very simple. So what we're trying to do, we're trying to make sure that vectors X, which is my word bird, if you remember, is close to the X itself, and that's my expected outcome should be close to fly, right? So if that's the case, if I'm successful and if I take dot product, this value should be close to 1 or getting high. And if that value is high, and if I take exponent of it and divide by the sum of all other possible exponents, I'm effectively estimating what we call probability of the word Y appearing next to X. Okay. So that's a sort of a well-known technique. And then what I do, I go through all my 44 pairs. This is size T is size of my training set, which we defined earlier, 44 pairs. And I compute these products for any given word that I choose. I go in that windows that I described earlier too. So for example, remember I gave you earlier, when was it? I guess here I was talking about fish, swim, fish, dip, etc. So for fish, in this case, I'll just look for 2 words, okay? And that's forming my summation, the first summation. And then for the next word, I do the same. And that's how I add up all these, sort of expected probabilities, if you like. And this is my objective function. I want it to be maximized, and maximization done in the standard way. It's a gradient descent. Usually we use stochastic gradient descent, but it's the same thing. I mean, it's not much different. All right, so that's basically how it's supposed to work. Now let me show you that this thing works. And now we start the demo. All right. So first I need to reconnect. Runtime before. Okay. All right. What you see on the street, sorry, on the screen, not on the street. What you see on the screen is a random placement of those 14 words just as a starting point. And now we're going to start our algorithm as I described it. And I made a slight mistake. I should have kept this to a smaller number, not 1,500. It'll probably take like, I don't know, a couple of minutes, maybe even longer, but if you feel uncomfortable, I can stop it. We don't really have to run it that much.
Well, yeah, I think the more iteration, basically, the better results, right?
Yeah, the
So,
better results. Yeah, if the audience doesn't mind, let's just wait since I already started it. But then we could play more experiments. I could show you on the next one that, you know, it will run faster.
so yeah, the thing is, these algorithms allow you like to continue the iteration before the results you got in the previous iteration. Like, you know, we are running 1500 at one shot. Let's say, you know, I run maybe 500 at the first shot, and then additional 500 and make it a 1000. So that additional 500, it will be based on the results you're getting from the initial 500, or it's starting from the.
No, yeah, you're right. Yeah, exactly. And it will end pretty soon.
Okay.
Okay, so here it is.
All right. Yeah, it's pretty good.
Now, yeah, as you could see, the separation is very clean. And you can read the words. You'll easily identify that, you know, the groups are distinct, just like I said earlier. I added color just to, you know, make it easier to see that they belong to different groups. And just like Professor, you know, Dr. Wang just saying a second ago, you don't really need to run that long. Maybe let me just run it one more time if you don't mind. I'll do it here, but I'll change this to 100. All right. So even though you see the point now, but I'd like to emphasize that it doesn't, you know, take that long usually. Sometimes it does, but usually it doesn't. All right, one more time.
So this is purely a mathematical solution, not using deep learning or anything like that yet.
Yeah, that's a very good point. But by the way, the algorithm we just went over, some people call it shallow neural net, but technically it's not really even neural net. As you could see, there was 2 matrix multiplications and that's it. A neural net by definition must include some nonlinearity, which we don't have here. Yeah, great question. No deep learning here, absolutely correct. All right, so what I'm gonna do now, I'm gonna run this by 100 epochs. Epoch is basically going through, just lost my position on the screen. All right, here we go. All right, so I'm gonna run this by 100 epochs, and epoch is basically one run through a data set. So we're gonna run through data set 100 times. Okay, so now you could see words started separating, but word bird is kind of outlier. It doesn't really, you know, sitting in the right class or in the right position, if you like. I can repeat. And now, as Dr. Wang was saying, we're going to add on top of what we just had a second ago. And as you could see on my second iteration, I'm done because one can draw a line this way and we have separated words. Okay. All right. So any questions about this particular demo or algorithm?
I had a question.
Yes.
How did we get our initial W0 and W1 matrices that we were using for this calculation?
Absolutely random.
Oh, all right then.
You may notice when I ran 2 experiments, I mean, I don't know if you remember this or not, but the layout was totally different for the one I'm showing here, starting point. Does this answer your question?
Yes, thank you.
Mm-hmm. All right. All right. Okay, so this was a demo. We just did it. Now let's go back to original problem. If you remember, the original problem was asking whether words can be identified by a machine in their meaning, right? And again, we stay in this new definition of meaning, which is appropriate for machines. What we'd like to do now, we'd like to, you know, sort of scale up the problem. I just gave you 6 very simple sentences, only like 2 topics really. But what about if we ask the same question, but about the whole corpus of English language? And of course, one may, you know, start asking questions. What do we mean by English language, right? What kind of, you know, set of words are we looking at? There are various ways to sort of assess number of words in English, but no matter what you look at, the number is going to be huge. Even if you take like 20,000, the average number of views used by a native speaker, it's still very, daunting task. And what happened was really remarkable achievement by Mikolov and his colleagues in 2013. He published 3 papers that year. 2 of them are shown here, and they talk about one particular algorithm, which is called skipgram. And we're going to discuss this algorithm next. But before I go into algorithm itself, I'll just mention a couple outcomes that came from this paper. And by the way, in that year, or a couple of years, I guess, around 2013, Mikolov was publishing first at Microsoft, then he did this, outstanding results published from Google, and then shortly thereafter, he moved to Facebook. That's why I was saying in my communication earlier that this research came from those companies. So what he did, he essentially used the same principle that we just looked at, but he made some very significant, he and his team made some very significant changes which allowed the algorithm to scale, all right? Before we go to those techniques, let me just show you what they were able to observe, and they showed it in their paper. One thing they claimed, and it was verified by many people many times after that, that once you build this embedding, they call it dense embedding. And by the way, their dimensions are very high. They go in hundreds, sometimes even thousands, depending on the task you're trying to solve, the problem you're trying to solve. But once you get to this very high dimensional embedding, you start observing remarkable results. For example, if you look at vectors man to woman, uncle to aunt, king to queen, they all very close. And moreover, you can write equations such as this: king minus vector man plus vector woman would be equal or almost equal to vector queen. Now, I must say it doesn't work exactly, because as you can understand, there are always some, errors, etc. But it does work very, very nicely, very close. They made a few additional observations. Some of them are shown in the bottom of the slide. If you add vectors Russia and river, you get the biggest river in Europe and in Russia, which is Volga River. If you add vectors Germany and capital, you're getting Berlin, etc. So what this allows us to do, you can now look at linguistics, or some parts of linguistics, as working with vectors. So for example, one could ask, what would be result of this equation, right? If you take vector France and add to it vector which is difference of Moscow and Russia, what do you think it's going to be?
Paris.
I'm sorry?
I think it's Paris.
Yeah, let's try. Let's see if that's true. So where was my? So I think we had what, Moscow and Russia, and we put France, right? Yeah, Paris came up. And you could play, with other combinations here, etc. So going back to my slides, yeah, that's exactly what's happening. As you could see, relationship between country and capital is somewhat similar. Again, just like I said, it's not exact. What do you think would be on the tip of this vector if I place, like if I start at Turkey and do, as a country, of course, and then do the same vector as I have for these 3? If I add to vector Turkey, the vector which is difference of country and capital shown above, what should be in this position, in your opinion?
It will be capital of Turkey, right? So, but I don't know which city. Is it Istanbul?
Is it Ankara? Ankara?
Yeah, the capital of Turkey is Ankara.
Oh,
And
Ankara. Okay.
yeah, that's what I would have thought too. And in fact, that's what I was thinking that would happen. However, if you go back to this little tool and now do Turkey, you'll see that the closest word different from Turkey is Istanbul. So Dr. Wang was correct. And
What
that
is coming up with
suggests,
largest city?
yeah, exactly. That's the point. Maybe when we look at these maps, right? Maybe the relationship captured by linguists and the naming here should not be capital, but the largest city or most important city, something like that. And when I say most important is in terms of, let's say, financial markets or something, a different aspect, just being, capital. Anyway, that's a kind of interesting observation, in my opinion. And let's see. Yeah, we just saw that. Yeah, so here is this, example from their paper. Basically, Ankara goes a little higher, and if you stretch this vector this way, it's going to be Istanbul, as we just saw.
I'm curious what city it comes up with for the United States.
Yeah, good question. Why don't we just play with this right now? Let's see. So should I put USA or United States? To be honest with you, I don't know the answer. Okay, so USA did not work very well. How about America? Oops, nothing for America. Okay, so one other thing I should say. Now, this particular program was trained by some individual, Anthony Liu, in 2016, and he may not have looked for pairs of words such as United States. So this may fail.
Right, it needs to be a single word.
Well, again, depends how you program. I mean, there is a way to do it for pairs, but he may or may not have done it. Yeah, it looks like, yeah, he didn't do that. I wonder if he allowed something like that. Nope. Yeah, sorry. We could try Spain, because I know this one works nice. What would be the outcome for Spain?
Madrid.
Madrid, yes. Yeah. Anyway, as you could see, it doesn't work always, and it's okay, right? It's not supposed to work as perfectly as we would hope, but it still works remarkably well. Now, let me tell you my sort of experience with this. Why I was blown away once I saw these, results. Not because of the paper. When I read the paper, I wasn't moved. To me, it's like like any other paper. There are so many papers you read, and when you try to implement, usually, unfortunately, they don't work. They might be very good ideas, but it's hard to make it really work. So at that time, I was working on a project where a client wanted to do some classification problem of whether certain events will happen related to their customers. And at some point during the project, they said, we have these notes taken by agents who are on the call with clients. Can you incorporate that data into this prediction model? And when I look at the data, it was very noisy. Like, for example, people would use acronyms or synonyms which are not known to people outside of the domain, or sometimes there would be even typos. And those were kind of really hard to deal with. And then since I knew about this paper, I thought, okay, let me try this technique. Let's see if this be of any value. And there was one tool available at that time. This was programming done in R. Once I tried it, I was really blown away because it worked. It was clearly correctly identifying typos, acronyms, etc. Because in the context, those might have been repeated several times, and therefore machine would learn them. And that way, we were able to improve our model. And from that point on, I was, very much interested in this topic to learn this specific topic deeper. I'm not trying to say that I know all the details, but the good thing is also, I should mention, in 2013, when these papers were published, Mikolov and team released code in C. So anybody who likes programming, you can find their code, and you could develop your own dense embedding and use it in your applications. So that's a great part of it. And later, we started using it for other, domains, not just words, not just languages, but even like, which nothing to do with linguistics. And these days, as I said, it's being used pretty much in any machine learning application. So this graph shows you the number of searches for word embedding starting from 2014. So remember, the paper came out 2013. It took a little while, I guess, for people to start, learning about it and putting in their applications. And then it was growing quite fast for some time until 2019. And then by that time, I guess everybody knew how good and important this paper was, and they knew the results. So the search starts going down. The reason it started going down, not because this is not important, but because the data science moved on. There are much more complex algorithms now, which also work quite remarkably. All right, so next I'd like to spend a few minutes discussing what did Mikolov and team really do? How did they turn this technique, nice technique, into a major technology? And to answer this question, you really have to go back and look at these formulas. Remember, this is our objective function defined that way, and the P, the probability, conditional probability defined in that way. So if you guys, let me just remind you, W is my vocabulary, and the length of vocabulary is shown here. And of course, T is the pairs of words, right? So if you look at this formula, can you tell me what's a problem if I try to scale this to 20,000 words, for example?
Computation.
Exactly. Just look at these numbers, right? Not only I have to compute exponents, which is a very expensive operation. So dot product is not expensive. I mean, this is relatively, easy to compute. But exponentiation is not easy at all. And then I have to do it not for one word, but for all my words in vocabulary. And that's a big problem. That's a very big problem. And of course, if I have to go through all of my, pairs of words, it's going to be even, more daunting task. So what Mikolov did, they done very nice breakthrough through, I guess, hard work and experimentation. They found two, key improvements. They sort of cut corners, because if you implement what they suggest, you're kind of ruining the mathematics, right? The equation becomes, from the mathematical point of view, incorrect. However, it doesn't really hurt the performance of the algorithm. In fact, they claim it improves. So what do they do? Well, first of all, they don't look at all the words, okay? They just do the training on the subset, and then they do the calculation, just like we described. And that's sort of one. Second thing, the two other points are shown here on this slide. They don't look at all the words as they appear. Instead, they sample frequent words according to a formula, which I'll show in the next slide. And moreover, they also add to objective function negative words, but in the right way. So what do I mean by negative word? Remember our example, like if I'm looking for, let's say, bird and fly, right? And in my objective function, I have dot product of those words, etc. What they're doing is they're saying bird should be close to vector fly. However, it should also be far away as possible from the word ocean. So that's the idea of adding negative words. And by these two little improvements, they were able to speed up the algorithm and improve the accuracy. All right, let me just show you how they do this subsampling. So what they're saying is this: if we get some word to appear very frequently, it doesn't really add much value if we keep using it over and over. So instead, let us define the probability with which we will be pulling the frequent word, and it's going to be essentially looking like this. We're going to take square root of this number, where t is something, let's say 10 to the minus 5. And this is our actual frequency of the word that under consideration. So the more frequently the word is appearing, then they put this cap on how frequently they will be pulling it, which kind of makes sense intuitively, but it takes I guess engineering genius to come up with this formula. Again, maybe I'm just a little bit too biased, too opinionated about this, but I was really amazed when I saw this. And the second part, the negative sampling, and let me just kind of explain it in this example. I hope it will be clear. So here, by the way, the formula, once you throw this negative sampling, it's going to look like that. But here's an idea. So if you're trying to, let's say, predict vector for, predict close vectors which are close to vector bird, or predict words which are close to word bird, you don't want the outcome to be ocean, right? Clearly, this would be bad decision. But for the negative word, you don't want the negative word to be close to bird. So that's the idea. And I'm just showing it here to you. If you follow the formula here, you'll see that if this case happened, if you're getting close to ocean instead of fly, for example, then your calculation would show you that that product and the log of it is very low, below 0. What you really want to do, you want to make sure a bird is close to fly, and the negative word is the other one. It's ocean, just sort of the opposite. And then when this happens, these values result in the objective function being close to 0, basically, increasing quite a bit. So that's a point I'm trying to drive here in this slide. I hope that makes sense. Okay. All right, so that's basically what they have done. And this allowed them to, just like I said, make this technology. And today it's being used in pretty much every application you look at, especially where NLP is present. All right, so as I mentioned, there are many more results along these lines. In the same papers in 2013, Mikolov and team describe another algorithm, which is somewhat analogous to the one we described in the results, not in the technique, it's different, but the output is very close to what we saw. Stanford guys developed in 2014 and published very nice algorithm, GLOVE. In fact, I used this one very first time when I tried. It was this one that blew my mind. This is a bit different altogether, but one can show that they achieve the same thing, even though the techniques seem to be different. And then going forward, people were coming up with more advanced algorithms. So fast text works on the subwords or characters that doing essentially the same thing. And there are many other algorithms, just to mention, star space, another one. And by the way, these two are coming from Facebook, if I'm not mistaken. And as you could see, every year or a couple of years, there's something coming in more and more. And today's hot topic is embeddings of graphs and networks, which I haven't even listed here. So I think this would be probably all I wanted to talk about. Do we have any questions?
Yeah, I have a question. Those methods, they already have a tool available on the website or something?
Yeah. All of these are already pre-coded and released.
Oh,
yeah.
Okay. That's interesting to see.
Yeah.
And also, could you give us a copy of the slides?
Yes, I'll do that.
Okay.
I'll email it.
Okay, thank you.
Mhm. Okay.
Yeah,
Right.
I think in terms of just my feeling, okay, so in terms of application, so those techniques developed specifically for the words characterization, probably be able to apply to other things as well, right?
Yeah,
maybe.
absolutely. Yeah. I already mentioned that even when we work, we apply this to different objects. But if you look, you can just type in not probably word embedding, because words kind of spells out what you're embedding. But you could look at graph embedding, which is extension, like it's one step further. It tries to capture more intricate structures into this embedding procedure. And you'll see that it is applied to many different things, like chemical, pharmaceutical area, all kind of network engineering. You could see it in many places today. Yeah, in biology, it's very, very popular when people analyze, biological elements in the biological domain of various
Yeah.
kind.
Yeah, actually, the most important part is kind of how you model your event, right? So it's kind of if you have some sort of a model, and then
Yeah.
you can put it into this algorithm, probably can automatically categorize different events into different buckets, right? So
Yeah, the very first thing that was happening after this paper came out, people started embedding first sentences, and there were papers which were claiming to do really well, and I'm sure they did. I just never had to do, work on that kind of problem. And then people were embedding paragraphs, and of course, right away, papers were showing up how you can embed documents. And the idea is quite simple, right? If you have like multiple documents which come from the same bucket, right, then you can sort of say, okay, let me train and make sure one document vector is close to another document's vector and do it the same way. Yeah.
yeah, very interesting. Yeah, I kind of immediately, like in my mind, I'm working in this 5G network, like these are maybe like a different network. You have, the performance-wise, so diverse. You kind of using different KPIs, right? So kind of
Yes, yes.
put the performance into some sort of buckets,
Right.
especially like, if for 5G, we have 3 different pillars, right? So kind of, depending on how you look at it, then from the throughput point of view, delay point of view, right? So then, yeah,
Yeah.
okay, cool.
And this has been used in the context of networks too, just like I mentioned. Yeah.
Okay, yeah.
Does it work to split things into more than 2 categories?
Yes, yes. Basically what will happen, oh, I forgot to show you one more application. Thank you for reminding me about that. All right, so this is, interesting demo. Basically, this is, what is this? 10,000 words run through Word2Vec, which is probably a skipgram algorithm. And they are rotating them slowly. I think there's a way to speed it up, but I forgot how to do that. Anyway, the point here is if you hover over any of these points, as you could see, it's showing a word, in this case, what, diagnostics. Again, because this is 3-dimensional, in theory, right? Of course, we only can see 2-dimensional, but this is 3-dimensional. It's hard to sort of capture the surrounding. But I think if I do it this way, let's see this, I did it somehow. So my point is this, these words, they're clustered. For example, if you have something, let's say from art, sports, and business, they will come up as 3 distinct clusters, just like we did in our example.
Yeah, that's cool.
Yeah, the challenge is you need more dimensions to separate them really well. In my example that I showed you, I had to end up with 2-dimensional because it was the easiest way to demonstrate without making it too complex. Yeah.
Is that in general number of a dimension equal to number of the categorization, like the number of different things, different buckets?
I didn't understand your question.
Let's say you have 3 things you want to categorize. It has to be using the 3-dimensional.
Oh, no. That's not what I said. What I said is, okay, even in our case, we could have done, let's say, 50-dimensional embedding. Okay, just for two, and it probably would have done better embedding in the sense that the vectors would be closer. Like technically, if you, what was the demo? If you look at this result, right? Technically, one could say, yeah, this vector is not really close, and that's fine, right? But my point is this: if you move to, let's say, 50-dimensional space, their vectors might have been closer. But however, what's difficult with the higher dimensions is to visualize. Do you see my point?
Right. The
Yeah.
point is to cluster them, not necessarily draw a straight line between them. Is that correct?
Exactly. If I did this, let's say in 4-dimensional space, and they clustered really well, there is no way for me to demonstrate it for you visually. The only thing I could do, I could list you 14, vectors, high-dimensional vectors, and ask you for yourself to go and check that those vectors are indeed very close to each other. That's a challenge. Just like in this demo, right? If I tell you that certain words are close, you just have to trust me, because you don't see them as vectors in 3-dimensional space. That's the thing. But to answer the question Yiping asked just a second ago, Dr. Wang, you don't have to limit yourself to 3-dimensional space. No. It's actually better if you go to higher dimensions.
Yeah.
For all practical applications, we always used, the lowest we used was 50. Dimension was 50.
Okay.
And there's a trade-off. The higher dimension, the longer the training takes. By the way, what Nikolov and colleagues did, they did the training on Wikipedia text. And it was, of course, running for a very long time, maybe weeks, if I'm not mistaken.
Yeah, cool.
All right. Well, any other questions? All right, if no questions, then I guess we could end.
All right. So yeah, I think going once, twice, gone. Okay. Thank you, everybody, for attending. Thank you, Dr. Kafizov.
Wonderful job, guys. Thanks. Appreciate it.
Thank you.
Thank you, Dr. Newman. All right. Bye.
All right, thank you.